and you had a process, how would you set up the inspection? So we call this measurement, we call that inspection. What are some ideas? How could we do it? How could we do an inspection process to meet our customer needs? What's the primary goal of inspection? And we want to meet our customer specifications, right? But what do we really want to do with our inspection process? So it's nice for us to know that we've met the customer specifications, but what do we really not want to do as manufacturers? So if the manufacturer gives us a tolerance like this, and we're producing the parts to within a capability of this, then maybe we could use a cheaper process to make the parts, right? So that would affect our bottom line, right? That affects our ability to make a profit. Okay. So what's the primary thing we don't want to do as a manufacturer? Ship crap to our customer, right? So we don't want to send crap to our customer. We want to make sure that nothing that leaves our loading dock, so shipping and receiving, right? At the shipping end of our loading dock, we want to make sure that every part that goes out meets our customer's needs. It is within our customers. And so how will we know? If I'm making 5 parts a day, then I want to make sure I don't send any bad parts to my customer. What am I going to do?
You're just making 5, you measure all 5.
If I'm just making 5, I'm going to measure all 5 of them, right? So especially this, one critical dimension on that part, right? I'm going to measure each part as it goes through. Now, what if I'm making 500 parts a day?
You can take a sampling of the parts and measure those.
So if I'm making 500 parts a day, I'm probably not going to. So what do we get paid for as a manufacturer? That it probably won't exist very long. Although I've seen that can go for quite a while on venture capital.
Meeting design specifications.
But what do we get paid for as a manufacturer? As a manufacturer, we get paid for sending invoices. Right? We don't get paid if we don't send invoices. What allows us to send an invoice? Doesn't necessarily have to be completed, but we have to have shipped the part, right? So when you buy something with your credit card, you're actually not supposed to charge your credit card until they ship the part, right? Not all companies are doing that. They're not actually supposed to get that charge on your card until they ship the part. It's like that. So as a manufacturing company, when we ship you the parts, then we'll have some arrangement that then we can ship you an invoice. And then you pay us for the parts. Now, if you're the customer, do you pay the invoice when it arrives? So what are you going to do? Oh, wait. These are all messed up. It's either the mat or the pad or one of the tiles. One of the tiles. So it's forward tile.
Forward tile.
Okay.
The customer's going to do their own inspection of the parts.
So customers might do incoming inspection, right?
Yeah.
And so you sampled, how many did you sample out of the 500?
Probably like 10.
You sampled 10, so you sampled 1 in 50. And you're the customer. How many are you going to sample in the incoming parts? Out of 500. So you're going to sample 1 in 10. You're going to sample 1 in 50. Because you guys didn't talk to each other about how many you were going to sample, right? In your specification, did you tell them how many you were going to sample? So to your vendor, you're the customer. You give them the specification, said all the parts must meet this spec. Now, just like the manufacturer, you're lazy. You're not going to measure all the parts, right? But you're going to sample some of them, and you've got a really persnickety receiving guy, so he samples a lot. Got a lot of downtime, maybe. Not too much else going on, no light. He's sitting there with his calipers measuring all the incoming parts. All right, so what do you do when you find one that doesn't meet the spec? Do you pay the invoice? No. Or you might pay the invoice with the whole back. You might pay part of the invoice, right? So there's some options here. But what do you want to do? You don't want that. Do you want that part that doesn't meet spec? No. He's going to come take it. He's going to either fix it and send it back to you or dispose of it. Because you don't want to be stuck with the cost of disposing of the part that doesn't meet spec either. Right? You going to rethink your sampling strategy? Probably. Because you guys, even if you both are sampling 50 parts, or you're both sampling 10 parts, it's not going to be the same parts, right? Okay. So one thing we can do is we can do a quality check at the end of the line before we ship the parts. And that's what we're talking about here. We're doing a quality inspection. I used to work for a nuclear power plant. So there's different grades of systems inside nuclear power plants. There's what they call nuclear safety classes. And so when you're nuclear safety class 1, that means if this part fails, it can affect the operation of the reactor. Right? Typically detrimentally. And so we don't like to affect the operation of the reactor detrimentally in most cases, right? Do you think they sample the incoming parts? They do 100% sampling on the incoming parts. We had a, it was actually kind of funny. So you can do, you do a process where exactly the same part that we took out. But the part that we have is equivalent to the part that we took out. Or we've modified our operating procedure to make up for the difference between two parts. So you imagine that it's expensive for these places to be shut down, right? In fact, like millions of dollars an hour are expensive for them to be shut down. And so, so we were coming off of a shutdown for refueling. There was a project that I got put on that at the last minute, it was keeping the plant from starting up. We had an automated solenoid valve that was supposed to be able to, open and close, little solenoid gate valve, open and close this line. And it's supposed to be controlled from the control room. And we didn't have none of those. But it wasn't working. It didn't open and close anymore. And you have to test all these things before you start up. And so they said, well, so this was at Vermont Yankee Nuclear Power. Yankee Road, just down the street, was the same generation as our plant. It was in the process of decommissioning. They had the same system, and their valve worked. So we're going to go steal the valve from Yankee Road. And it's going to take a 2-day process to get it out of there, bring it in, inspect it, and get it installed. We can replace it with a piece of pipe. And then change the operating procedure where the reactor operator has to come inspect something and adjust the valve manually if it's downstream or upstream. I don't remember the thing. So we write our proposal to the NRC to replace it with a piece of pipe. We didn't have any pipe that was inspected to nuclear safety class 1 in stock. But we did have steel rod. So we made it. And when it started off, $8 million. Everybody's happy. All right, so sometimes we have to do 100% inspection. Sometimes we can do sampling, like we said over here. And so we don't want those nuclear safety class things to fail. It's bad. They fail. All right. So quality inspection, make sure we don't ship crap to our customers. That's one thing we can do. Why else would a manufacturing engineer matter? Why else would we measure besides quality inspection? Lord Kelvin tells us that to measure is to know. So we know that we have good parts. What else can we do with the measurement? He said know that it's a good part.
You said earlier, maybe we can make manufacturing process more efficient by larger tolerances.
Okay, so we could understand our process better and make sure we're using the right equipment to meet the customer specifications. so that we're not making parts that are much better than the customer wants. So that's one thing that we can do, is we use it to understand our process. What else can we do with it? So if I'm measuring parts, say we got our example of a turn part like we used last week. We've got our turn parts coming off there. And so we've got our process tuned, so it's making the sides parallel. It's making the surface finish that we want by adjusting. So what should we control to make the surface finish come out what we want? So we have this side of the British stamp. What should we adjust if we want to adjust the surface finish on our turn part? Yes.
Your feed rate.
We can adjust the feed rate, or what other parameter can we adjust that we have easy control over? The speed won't work if we're talking about feed in millimeters per revolution or inches per revolution. So if we're talking about feed in inches per millimeter, then those speeds are affected. Or inches per millimeter, inches per minute. That's not going to have a significant impact on our surface finish. It may impact the stability of the process and chatter and things like that, so it may have some impact, but it won't have a significant impact on surface finish. What are the two parameters that impact surface finish on our turn parts? So feed is one of them. The parts look sort of like that, right? But somebody said, right? Tool is radius. So the radius down here at the bottom of these valleys, and then the space in between those peaks, that's going to have the most significant impact on our surface finish on our turn part. So we've got surface finish dialed in, our customer likes it. We've got diameter and parallelism dialed in, our customer likes it. We're measuring our parts, and all we're doing is making this one diameter. We're measuring our parts, and Kyle says, hey, stop loading the truck. This one's too big. What do we know now? Well, maybe he got 10 in a row that were too big before he says stop loading the truck. So what do you know, Kyle?
Tools wearing down.
We will suspect that maybe the tool's wearing down, right? So as the tool wears out, the parts are going to grow. So why is Kyle standing at the loading dock? Oh, because we hired him as a quality manager. Quality manager to make sure we don't ship crap, right? What else could we do with Kyle? Where else? Go ahead.
Now that the parts are coming out, so we can do it time-based.
Yeah, what if we have Kyle teach Brian how to use a pair of calipers or a micrometer? And Brian is the machine tool operator. He's dressed like a machine tool operator today. And Brian, what are you going to do every part you just take out of that lathe?
I want to check them all, but
How long does it take to measure diameter for the caliper? What if it took a long time? It takes more time to turn the part than it does to measure diameter of the caliper, right? So you got some downtime. You sit there drinking Mountain Dew, you can measure a few parts, right? So is it enough for Brian just to measure them? I mean, so Brian will know now immediately if he's making parts that are too big, right? If he's outside the tolerance, as Kyle said, stop the lathe if the part gets over this diameter. Brian will know immediately he can stop the lathe, and the emergency stop, sound the sirens in the shop. Everybody will come running to find out what happened to Brian. Is it enough for him simply to measure the parts? So we have a very limited scope of interaction today in class. Kyle, go ahead.
No.
What do you want? What else do you want Kyle to do for Brian? Kyle, what else do you want Brian to do as he's measuring the parts?
I want to track all the measurements like over time for each part.
Yeah.
And chart.
We would like him to not just measure the part, but to record his measurements, right? And so he's recording his measurements, and he's going along, and so we've got an upper limit and a lower limit. And you see here, we call those upper control limit and lower control limits. That is drawn right on the graph. And so maybe you've got a micrometer that's got a serial output, And all you do is press the button and it shoots it over to Excel. Wouldn't that be sweet? Those are pretty cool. Because then all you got to do is actually know how to operate the micrometer and get consistent measurements. And so as you look at this graph here, what do you know about the process? It looks like it's fairly well controlled, right? So we've got some, and so the variation from point to point, what is that telling us? Point to point variation in our process. It looks like we got a little wave going on here that may be telling us something else. Yes?
It's not consistent enough to just be
Pat or Matt?
Pat. It's not consistent enough to just be from tool wear.
So that's probably not from tool wear, is what it's telling us. So what happens when we measure the part? How do you measure a part with a micrometer? Hold it in your hand, you put the micrometer over it, and you go squeezy, and you go like this maybe to make sure that it's in flat, and you go like this to make sure that it's the same on your part, right? So one thing that's going to account for some of this variation here is how hard Brian turns the knob, how well it's aligned square to the caliper. And so that's a factor of measurement uncertainty, right? So we don't know what the number is. We know it's something like this, right? So there's what other factors? So we've got operator variability. Now, what if Brian's not the only operator? What if it's Brian and Connor? Who's probably squeezing, and what if we're using a caliper? Who's probably squeezing the caliper harder? Connor, as he works out. Okay. So we get operator to operator variability. Now, what if I measure the part here as opposed to here? We get location to location variability measuring the same part. And all we're trying to do is measure it in diameter. What if it's a more complex measure end? Right? So we've got part and part to part variability. Right? Not all the parts are going to be the same, even if we're able to measure them all the same, right? So we expect, every time we have a control chart like this, we expect variation, right? And if you see some sort of a regular signal in there, then you might be able to learn something about that variation. Maybe this was a surface roughness thing, but this company that we looked at, they kept having parts out of spec, but only at a certain point in the day. So the parts would be in spec all the time, except like between 1 and 1:15 every day, they get a couple parts out of spec. And they could not figure it out because the process seemed like it was in control, except for that time window. And so they call in the consultants to come look at the process, try to figure out how can our process be doing this, right? And all you have to do is stand in the room at the time when the parts were going out of spec. That's when the freight train went by every day. Right? You got to look at all those kind of things influence your measurement system as you go through. So we can do quality inspection. We can keep from shipping bad parts to our customers. We can do process control where we keep from making bad parts. So our tolerance should be somewhere up here. So when we get to our upper control limit, if our graph is tending towards an upper control limit, then we've got some information about the process, probably the tool's wearing out. So what we can do when we get to that upper control limit, so say our trend went like that, we get the upper control limit, what should we do to our process? We could change the tool, what else could we do? We could adjust for tool wear in the lathe controller, right? So we can adjust the program for tool wear. So those are things that we can do to keep that process in control. Which one should we put more effort into? Quality inspection, so not shipping crap to our customer, or process control? Kyle?
Process control.
Because that means you get to take longer breaks.
Yeah.
To do the quality inspection engineer. Yeah. Why else would it be?
It's going to end up saving you money in the long run because you're not going to make bad parts.
Right, so
Or as
we're not
many
gonna make any
bad
bad parts.
Yeah,
So does our customer, what does our customer pay for?
good parts.
Good parts. Does our customer pay for quality inspection?
No.
No. Is quality inspection a waste as far as our customer's concerned?
Yes.
It's a waste process, right? It's non-value added. So it's something that we have to do if our process is not in control. But if our process is in control, we don't have to do any outgoing quality inspection. And does he have to do incoming quality inspection? I mean, it's a nuclear power plant, yeah.
Yeah.
But if you're XYZ Widget Corporation, you have to do incoming quality inspection.
No.
When do you not have to do incoming quality inspection?
When your manufacturer is very good at process control.
When you believe, right?
Yeah.
You believe, right? When you believe that your vendor is not going to ship you bad parts. Now, you can be sneaky too. You can require him to do quality inspection, outgoing quality inspection. You can define his sampling that he must do, and you can require him to send you an inspection report along with each batch of parts. Now, does our customer care about quality inspection? And what are you going to do when our customer demands that?
What would I do? What would I want
Besides
to
meet
do?
the demand, right?
Yeah.
You're going to change the price.
Right.
Because now your process is more expensive. Now, unfortunately, what you didn't know is that he's Dell Computers, and he can eat you up for price. So you're not going to get the high price on him. But this is what we do, right? So if the customer is willing to pay for that quality report, that quality inspection report, then you can charge a little bit more for the parts. If they're not willing to pay for it, then just don't make the bad parts. So we'd like to not make bad parts. So we can measure diameter. What else can we measure? Measure surface roughness. Anybody know how?
And dragging a needle across the surface or something?
So we did. So actually, the very first way that we measured surface roughness was to take a microscope, an optical microscope, and it had a very limited focal field of view, so limited depth of field, and so you can focus on the peaks of the surface, and you have an incremented knob for bringing the lens down, and so you can count the peaks at this level. Come down to another level, count the peaks at this level, come down to another level, count the peaks at this level, come down to another level, count the peaks at this level. That was the very first study of surface roughness that was ever published. That's how it was conducted. Now, they get tired of doing that. What do you have to do? Count the peaks, right? They didn't have fancy computer algorithms back in the 1900-somethings to do that. So by the 1930s, what they figured out is they could take a record player needle and drag it across the surface, and it would ride up and down as it went over stuff. Now you can sample the surface by taking a profile across it. And that's kind of cool, because the other thing that we had in the 1930s is RC circuitry. So you could do math in a circuit, which is pretty cool. So you could do this, and you can have your little device spit out a number that's based on that signal that is running across there. So that's kind of cool stuff. So we can measure surface roughness. What do you want to watch out for? So what's the lateral resolution of sampling when you drag across like this? What's the minimum lateral resolution? What's it going to be based on anyway? It would be based on the radius. So your profiler stylus looks like that. A little radius at the bottom. Typically like a diamond. The radius might be 5 micrometers. So that's a typical stylus profiler, drag across there. So if the points are more or closer together than a spacing of like 5 micrometers, you're riding on that radius, right? So you lose some fidelity right there. It's not a perfect point. Okay. What else can happen in this process where you drag a record player needle across the surface? We deform the part, yeah. What else? So why would we deform the part?
Or stylus.
What's stress equal? Stress equals force over area. And so if we want more precision, we need less area, right? But the less area we have, the higher the stress goes up. So that's a problem. So what else happens? What if we're in a hurry? We're cranking up the speed on the motor, right? And then our tip becomes airborne. And then it lands. It becomes airborne again. And then it lands and bounces, right? So how do we overcome that? More force, which again increases stress. And so if here's our stylus tip, these are the problematic issues. You see what it does to a hardened aircraft aluminum surface. So you're machining the surface with your stylus tip as you drag it across there. Oopsie. But who cares, right? So if you're making measurements this way, do you care that you're deforming the part? Or actually you're machining the part here, you're plastically deforming?
Yes, because that deformation.
You have to use a scanning electron microscope to find that scratch.
Yeah.
He's not going to see it. So you don't have to worry about the scratch that you made. It's actually really hard to find it even with the scanning electron microscope. Do you care? You don't care as long as you're using exactly the same equipment he's using, right?
Yeah.
Because he's made the specification. In fact, he's used that equipment, presumably, to determine what the tolerance is that he can accept for a good part. Practice, we have to doesn't, because you can. But in reality, you should have, right? You could have done an experiment to determine what's the right surface finish. As long as you're using the same type of equipment that he's using, and you're using in the same manner, then you can still control your process to give him parts that you accept. Correct? Right? But you should understand that the part that you're getting, you can never measure that surface. You can never measure anything. All you can measure is the interaction of your sensor with the thing you're trying to measure. And so if you try to measure it with an optical instrument and you're measuring with a stylus profiler, you will not get the same numbers. Guaranteed. The way they do the math on this is actually kind of interesting, because here's what the raw signal kind of looks like as it comes off there. And so you'll notice one thing here is that this scale is what? Millimeters, 5.4 millimeters. So this is about 6 millimeters, and this is about 10 micrometers. So when you present one of these graphs, so this is a smooth surface, in case you're wondering. It's got about a 10 micron max roughness value there, so you can come across it. Oh, yeah, you can also measure surface roughness like this. Did you know that? Did you know that your thumb can detect about a 10,000th of an inch in surface roughness right here on that? And this is the test that the U.S. Navy uses when they're buying nuclear submarines. I imagine not all the components. Some of the components. So it's kind of a pain to analyze this signal. What's the first thing you want to do to get a signal like that? You have to do some math about it. Everybody's had like a basic W class, right? Do some work controls. What's the first thing you want to do when you get a signal that's doing this trending uphill? So why do you think that trends uphill, by the way? Do you think the part was growing? My guess is the part was a little bit crooked relative to the measurement equipment when you measured it. So what's the first thing you want to do? Yeah, you can dial it in, but you can fix it in math. Right? First thing I want to do is I want to do a best fit line for this signal. And I would subtract out the best fit line. And so what I've done then is I've made it level, and I've made the mean value 0. So if I make it level and I make the mean value 0, now it's a lot easier to do math with, right? Okay, and then I can figure out things like What if it's got a sine wave in it? And it's going uphill. It'd be kind of cool if we talk about the sine waves separate from the roughness, right? So the little ups and downs, that's the roughness. The big ups and downs, we call that the waviness. So if we want to separate the waviness from the roughness, we use some sort of a filtering algorithm. And so in this one, we used actually two different filters. One of them is a simple RC filter, the other one was a Gaussian filter. And same measured profile, so the same data set, two different filters. The average roughness, so that's the mean distance, or that's the mean distance of each point in the profile from zero. That's average roughness. That varied by 41% by simply changing the filter type on the same measured surface. So what are you guys going to do? If you want to work together, because you really want to buy these parts, right? Why do you want to buy these parts? Because you don't want to make those parts. You have decided it's a strategic decision of your company to outsource those parts to Kyle Incorporated. Kyle Incorporated really wants to make those parts, right? Why do you really want to make those parts?
We get paid to make those parts.
Yeah, both payments make, right, Kyle?
Yeah.
Right. So you're too lazy. You got a boat you want to pay for, right? So what are you guys gonna do? You're gonna talk to each other and make sure you're using all the same filters, the same type of equipment. Using different type of equipment, you need to figure out. So would you believe that the differences between the different type of equipment are typically systematic differences? At least on that particular surface, so you can figure out what's my machine read when your machine reads a good part. So you have that conversation with your supplier, between suppliers and vendors. All right, so we can measure diameter or length. We can measure surface finish. What else can we measure? What else do we measure? Hardness depends on what the customer specifies, right? So we can measure anything that we put a tolerance on, right? So we can measure hardness, we can measure conductivity, we can measure color, put numbers on color. What else can we measure? So we can measure strength of material, we can measure failure strength of component. That would be a destructive test. We could non-destructively measure elasticity, right? All right. So is there any other reason that the manufacturing engineer might want to measure stuff? Okay. I'm satisfied. So we want to measure stuff to not ship crap to our customers, and we want to measure stuff to not make crap. And preferably the latter, right? We'd rather just not make the crap, then there won't be any question about shipping it. Now, we talked a little bit about measurement uncertainty. What are factors that go into measurement uncertainty?
Repeatability.
So one thing that we'll talk about in the area of measurement uncertainty is repeatability. So what do you mean by repeatability?
Being able to measure the same dimension twice.
Okay, so measure the same dimension twice.
I'll get the same result.
And get the same result.
Yeah.
That's precision. our ability to measure the same thing twice and get the same result is called precision. But, well, if we can measure the same thing twice and get the same results, then we're thinking precision. What did you mean exactly by measure the same thing twice? Describe the measurement technique for measuring the same thing twice.
So,
I'm sorry to put you on the spot.
No, it's okay.
You could pass it off on one of your classmates if they're willing.
So in the case of like using the micrometer, would be measuring, say, the same diameter twice with a micrometer at the same point.
So you'll take your workpiece, you'll take your micrometer, measure it, put it down, pick it back up, and measure it at the same location. Now, how precisely will you be able to realize the same location?
Not very.
Pretty good, all right.
Yeah.
So there could be part to part, or like on the same part variation that's happening in that case then, right?
Yeah.
But more than likely, variation there is telling us something about your ability to use the micrometer, right? And so is twice sufficient? Wouldn't be very scientific to just do it twice, right? If we did it 3 times, then we could calculate a standard deviation. But it wouldn't have very much meaning, right? So maybe we'll do it 10 times. And once we do it 10 times, what do we want to do? We should plot it. I'm not sure plotting would be the first thing I did, although I'm an engineer and I'm kind of a visual thinker, so I like to look at graphs. So I might plot it first. Well, besides plot, what would I do? Find an average, right? So it's fairly likely that the average of all those measurements is the true value, right? Depending on how many measurements we make. If all of the error in the measurement was due to operator error, like operator inconsistency. If 100% of the uncertainty was from his ability to use the micrometer, then if you do a bunch of measurements, it averages out, as long as he's not systemically using the micrometer wrong, might be the true value. So precision is closeness of measurements to each other. Accuracy trueness is closeness of each individual measured value to the true value. Now, when we talk about measurands, what's the true value? How long is an inch? What do you think? How long is an inch? Anybody know? 25.4 millimeters. Is it exactly 25.4 millimeters? God, you said no. Stand up if you think it's exactly 25.4 millimeters. Nobody else? Stand up if you think it's not exactly 25.4 millimeters. At least everybody, well, Connor's trying to stand up. At least everybody has an opinion today. I really hate it when some people remain seated. An inch is exactly 25.4 millimeters. You know how I know? Legislated by Congress in the 1880s. You think we don't use the metric system in America, but we do, inch by inch. All right, but how long is a millimeter? Tenth of a centimeter. All right. So if we, because I said our trueness is the closeness of our measurand to the true value. How do we know what the true value is? So they used to have a meter. They kept it in France. And we used to have a foot. We kept it, I don't know, somewhere in the U.S. And both of those were a piece of gold. the meter seems more valuable to me. A piece of gold with some lines scratched on it that were a meter apart or a foot apart from each other. And so you can have your meter stick or your ruler, and you can send it to the testing lab that has that meter, and they can measure your ruler for you. And they can tell you how long your ruler is compared to their meter. Now, what do we have to do when we do that measurement? We control for temperature, right? So that piece of gold is going to do this. Why do they use gold? Says the fact that gold is cool. It's extremely chemically stable. It will stay gold for a long time. But it has a high thermal expansion coefficient, and it's kind of soft overall. All right. Is that how they calibrate yardsticks these days?
It's based on the speed of light now.
Yeah. So we do our light measurements based on the time it takes for a particular wavelength of light to travel a particular distance, or the distance that the particular wavelength travels in a certain amount of time. So all of our light measurements are based on the speed of light right now. And is that better or worse than the gold? I would argue less expensive. You have to have really nice light measurement equipment. But we could only have one meter. If we had more than one meter, then there would be inconsistency between the meters. Right? So when we had a meter, we could only have one of them. And according to our understanding of physics today, light travels the same speeds as long as it's the same atmosphere. I think we use vacuum. We actually do it in vacuum also. So as long as we're in vacuum, light's going to travel the same speed no matter where you put it. As long as you get the right wavelength. And do that. So now we can have more sensors that are qualified to calibrate our stick. They send it back with the measurement report. Tells us how long it is and what their measurement uncertainty was. Now we know something about our measurement stick. And so if you've got yours calibrated, and you've got yours calibrated, and now you guys can talk to each other. Right? So why do we want to do this? Why do we care about all this stuff? Right. So we want our company to be profitable. The way to be profitable is to promote commerce, right? So we want to be able to promote commerce between companies. So that's why we care about these different things. My work's fast. It's about the same. Okay, we got like 2 minutes left, right? 3 minutes left? Okay. So you guys are all familiar with math and normal distributions, right? So a lot of this math is easier if we assume a normal distribution. You've heard that before, right? Math is always easier if you assume a normal distribution. All right, so if this is the specification for our parts, and this is the observed capability of our machine tool, can we make good parts? So what's the problem here? Can we fix this process? Because it's a bias, right? Right? All we got to do is tell the manufacturer, no, we're going to make the parts this big. Got to tell the customer, right? I don't know, it depends. Connor, can you do that? If you're dealing with an FTP, you might be able to, right? No, sorry, we're going to make them this big. You can change your design. But no, typically you can't do that, right? But if this is your problem, then there's a good chance you can shift this down. And so probably what's going on here is you have the wrong setting, right? You programmed the wrong, if this was diameter, you programmed the wrong diameter. If you just make that adjustment, it'll shift down, or your tool's not the size you think it is, and you can shift that down. All right, so our trueness is this distance, right? Our distance from there. Okay. Now, what if oh wait, oh, it's on here. So I can draw on the paper. Look at this some way to point to the board. That's our design range. Brian says we can make good parts, but it's going to be real expensive to make. Why? The manufacturer has to follow a tighter tolerance, but they understand the capability of their machine will make parts like that, right? Yeah. Right. So if these are too big, if one tail is too big, maybe you can rework those parts if you measure them. If this tail is too small, maybe you can use those parts for a different product, but not for this product, right? What's that? Paperoids? If anybody ever visited a manufacturing facility where they have the nice glass case in the lobby where they don't have the pieces in there? You've all seen one of these, right? Or if not, you can picture it. Somebody asked me about when I visited the people that make cigarettes, the name of the company there. They own the disco or something too. Anyway, somebody asked me about that. Let me tell you something about all those parts in those glass cases. If the customer would have paid for them, they would have shipped them. Those are all out of spec. All right, I think we're done for today. The next class way to come in here. So you guys are doing 5-axis machining this week in lab. You should workshop getting the cam done early in the week. And you should reserve at least 30 minutes of machine time once you're certain that you know you get the cam done. The 5th axis unit is on the VM2. Reserve machine time on the VM2. The 5th axis unit is being bolted to the table as I walk over here. It's ready to go when you guys are ready to go.